I have just come back from holiday. I went to Spain to see the total eclipse of the sun. It's something I've wanted to do for a long time. I missed the opportunity in 1999 to see a total eclipse that was visible from England. So I took the opportunity to go to Spain on August the 12th to see a total eclipse of the sun. Now, I'm not alone in wanting to go and see a solar eclipse. There were lots of people in Spain for precisely that purpose. And I expect different people have different reasons for wanting to see an eclipse of the sun. It's beautiful, so it's an interesting event to see. It's not particularly common. It can be years between eclipses, although they do come in bunches apparently. And it's slightly risky. Shortly before total eclipse, shortly after the eclipse had started, a cloud came in front of the sun and hit the sun. And it wasn't certain that we were going to see the eclipse. We may have gone to all that trouble for nothing. So there's lots of attractive features to the solar eclipse. Plato, the Greek philosopher, thought that the sun was the centre of the universe, and so he thought it had special significance to us as travelling around the sun. That view fell out of fashion, and the controversy over whether the sun was or was not the centre of the universe raged right through the Middle Ages, with Copernicus and Galileo championing the idea that the Earth went round the sun. So one way or another, the sun has been significant to us. We turn to it as sunflowers turn to it. The sunflower famously turns to face the sun, and that's why it's called girasol in Spanish or French. It's the flower that rotates to face the sun. So all of these reasons are reasons for people to go and look at the sun, particularly during a solar eclipse. And for me also, the solar eclipse is of particular scientific significance, and I want to talk about that today. Well, first of all, what is a solar eclipse? Well, the sun is a hot ball emitting light, and I've put around the outside there's a glowing cloud of lighted gas known as the corona. And the corona, generally speaking, you can't see the sun. If you look at the sun directly, you'll damage your eyes, so don't do it. But because the sun is so bright, you cannot see anything close to the sun, except during a solar eclipse. The Earth is travelling around the sun, and the moon, these are not to scale. The light from the sun casts a shadow, the moon casts a shadow, and there's always a shadow behind the moon where the sun's light doesn't get to, but it happens that in the process of moving around the Earth, the moon, occasionally the shadow of the moon falls across the sun. the shadow of the moon falls across the earth, and if you stand in that shadow, you cannot see the sun. It's an accident of geometry that from the earth the sun and the moon look the same size, and because they look the same size, when the moon comes in front of the sun is hidden, and more importantly, all of the light from the sun is hidden, and the corona, which is normally invisible, becomes visible. So that's one, for scientists, that's one of the interests of the eclipse, is that they can study the corona. But back in the beginning of the 20th century, the total solar eclipse of the sun in 1919 was used as a crucial experiment. There are obviously in the background, far away, stars in the sky. That we can not see during the daytime because the sun is too bright. During the total eclipse of the sun, those stars become visible, and it's possible for astronomers on the Earth to look to see where those stars are. Now they know where they are in the sense that they have star maps of the sky, and they know in which direction at a particular time, they know in which direction they should be looking to see a particular star. Stars are visible in specific positions that have been mapped since the time of Tycho Brahe 500 years ago. Astronomers were mapping the skies, locating the position of stars. Now, let me tell you a story, because the story begins here really. One of the predictions that were made by Einstein as a result of relativity was that the light of the stars that are behind the sun would be bent by the gravity of the sun. What that means is that a star that's normally behind the sun, or was in a position behind the sun, should not be visible, but if the light was bent around the sun, it would become visible to an astronomer on the Earth. So the prediction that was made was that the star that was behind the sun would appear to be over here, because the light from the star would be bent by the gravity of the sun, and this would be visible during a total eclipse. And for this reason, Eddington, the astronomer royal, went on an expedition to Latin America to view a total eclipse of the sun, and to discover that light was bent by the gravity of the sun. The story that I'm telling you is that the general theory of relativity predicted that light would be bent by the gravity of heavy objects, the sun being a heavy object. Astronomers went to view a total eclipse so they could see whether or not the light was bent around the sun. And they discovered that light was bent around the sun, and this was a crucial experiment in differentiating between Newton's theory of gravitation and Einstein's theory of relativity. And because it was seen that light was bent around the sun, then that was a crucial test of the theory of relativity. That's the story, and that's the story as it's often told. That's the story of a paradigm shift the old paradigm, anomalies crop up, like the gravity shouldn't bend the rays of light, but it does, and so that test speaks in favour of the new paradigm, and scientists gradually or suddenly switch over from the old paradigm, Newtonian physics, to the new paradigm, relativity. Now, why am I telling you all of this? I'm telling you this because this is a simplification. Scientists like to tell you that it's the simple rejection of one theory over another. But before we do that, before we swallow their simplified story, you need to understand when it was suggested, who first suggested that light might be bent by the gravity of the sun. And the answer is it was Newton. Newton himself saw the possibility that light would be bent by the gravity of heavy objects. In fact, he went so far as to predict that some bodies would be so massive that light could not actually escape from them. Newton himself predicted black holes. So the question is not whether the light is bent by the sun or not, it's how much it's bent. And so the measurement of how much the light was bent by the sun became crucial to the test between the two theories. So the simple theory that many people will hold from their view of science is that there was an old paradigm, gradually anomalies accumulated from using that paradigm, and as those anomalies built up, eventually people were persuaded that a new paradigm was needed, and that one of the classic points in history where an old paradigm was replaced by a new one is when relativity replaced Newtonian physics. That's an oversimplification, and it's important to understand that it's an oversimplification because we have transferred that language. We've taken Thomas Kuhn's idea of paradigms and we've transferred it to the social sciences. We've started talking about we need a paradigm shift here, or we're seeing a paradigm shift as things change suddenly. And it's not as simple as that. In particular, it's not as simple as simply problems accumulate with the old paradigm. They might do, but let's have a look at one of the other anomalies. The Earth, as we know, travels around the sun. It travels in an ellipse, and the sun is at one focus of the ellipse, so that this is an exaggerated eccentricity, this ellipse, but sometimes the Earth is closer to the sun, sometimes it's further away, but it travels around. The point I'm going to make is this distance when the Earth is closest to the sun is called the perihelion. Now the Earth does not follow exactly the same path every time that it goes around the sun. It moves so that that perihelion gradually moves so that the perihelion here gradually moves to a new position. It processes. And that's been known about for a very long time. Astronomers have been measuring the position of the Earth relative to the sun, relative to the stars. They've understood for a long time that that happened. But they didn't know that it was an anomaly. They didn't know that relativity could explain that and Newton's theory could not. They just thought it was strange, but it was only when Einstein specifically developed a theory of relativity to explain how the Earth moves around the Sun and how it's changed by the speed at which it moves, because it moves faster when it's near the Sun and slower as it comes out again. Only recognised that that was a problem with Newtonian physics when it was shown not to be a problem for relativity. So the new paradigm serves the purpose of identifying the anomalies. It's not the case that scientists keep a notebook and say, here's an anomaly, and those anomalies eventually add up to, we need to look for a new paradigm. The new paradigm helps them to identify what the anomalies are. Now, why is that important? Well, it's important because the new paradigm arises out of, builds upon what is known within the old paradigm. Scientists don't take everything and throw it out just because they've got a new paradigm. The new paradigm has the characteristic that it explains the old paradigm. Now, that makes it very difficult to see paradigm shifts in science, and it makes it even more difficult to describe them, because much of Newton's physics remains in a slightly altered form within relativity. And so there is a kind of sense of progress. And that's something that we're really lacking when we talk about paradigm in the social sciences. The sense that the new paradigm builds upon the old one. The new paradigm is preferred because it explains everything that the previous paradigm explained, and some more, and a bit more. And we tend to use the word paradigm in the social sciences as it's just a different way of looking at things. It's a different lens to view things through. It's a way of interpreting the world, covers the same events, but there's not a sense of progress in the development and design of social science paradigms. And that, I think, is something that is missing. I think we need to think about that carefully, because in talking about science, and in particular when we add the word Western, we're talking about Western science. It's presumed that there's no real sense of progress from previous ways of knowing to the way that we're knowing. Of course I'm not saying that Western science is perfect. Western science, the very fact that we have paradigm shifts within science and will expect to have future paradigm shifts within science, means that it's never perfect. But there is a sense in which there are slight improvements, one paradigm over another, and that's been lost. That sense has been lost in the way that we talk about paradigms in the social sciences. We talk about paradigms in the social sciences as though they were arbitrary, a choice between them was quite arbitrary. No, there are criteria for deciding that one paradigm is preferable to another, and one of the key considerations is that the old paradigm gets subsumed within the new paradigm in a way that means that the new paradigm can explain everything the old paradigm did and a bit more. And so the old paradigm, in this particular case, Newtonian physics, said light will be bent by the sun. The new paradigm said, yes, not only will it be bent, it will be bent by this much. And this is exactly how much is going to be bent. And when you test, you discover that it's bent the right amount by relativity, not the right amount by Newtonian physics. And when you go back and revisit the perihelial motion, you discover that, well, relativity can explain that perihelial motion. It had been there for centuries and nobody had much bothered about it. It's the same story as I've said to you before as a research gap. Research gaps don't exist. They're made. Anomalies are not found. They're made. You make the anomalies by proposing a new paradigm, and the new paradigm shows you what is the key evidence to look for between the two paradigms. And so that's what I wanted to say about paradigms particularly, is people who talk about paradigms but who haven't looked at the science, the scientific developments that Thomas Kuhn was looking at in the structure of scientific revolutions, and the phenomena that he was using the concept of paradigms to explain, people who haven't looked at the science tend to think of, oh, a paradigm is just, we've got structuralism, we've got functionalism, we've got conflict theories, it's just another way of looking at things. No, it's not. There are paradigms are shifted because of evidence. New paradigm is proposed, the new paradigm identifies the questions that we should be asking, and the new paradigm offers the tests that it will withstand in order to justify itself. And as a result of that, at the end of a paradigm shift, we know and understand a little bit more than we did before. And that, I think, is extremely important in terms of how we think about paradigms.